Okay, good afternoon, everyone. We have the great pleasure to welcome today Professor Rafael Pelegrini Soares. Professor Pelegrini Soares holds a master's degree and doctorate in the chemical engineering from the Federal University of Rio Grande do Sul, where he is currently associate professor and head of Department of Chemical Engineering. He won an award from the Society of Chemical Engineering, ABEC, and the Petrobras Technology Award. Professor Pelegrini Soares has experience in process simulators. His interest in the development of thermodynamic models and computational codes for the prediction of properties of specific misturas for industrial application. He was the main developer of the ENSO simulator, which today has more than 200 registered users, and collaborates in the development of a simulator called EASY. He coordinates the creation of the COSMO-SAC-Phi, F-SAC, and F-SAC-Phi models, and he also collaborated with the development of the mixing rule SCMR. So once again, welcome Professor Pelegrini Soares. Thank you so much for being here, and please feel free to start your talk.
Thank you very much, Marlon, for the kind introduction. Let me share my screen. I'll share the desktop. So thanks again for having me. Thanks, Marlon, for the introduction, Fred, for the invitation. I'm very glad to be here to talk a little bit about COSMO-based models and the applications in high pressure or in compressible fluids with the model COSMO-SAC-Phi. I hope you are all well. We are all at home, mostly, at least. I came from the Federal University of Rio Grande do Sul. It's in the southernmost part of Brazil, here in the bottom. We are actually closest to Uruguay and in Argentina than Rio de Janeiro. And in our group, the topics of interest are mainly predictive thermodynamic models, cubic equations of state and mixing rules, a little bit of Ceph-based equations of state, and mostly activity coefficient models with F-SAC, COSMO-SAC, UNIFAC, and other similar, and more recently with the COSMO-SAC-Phi model. But we never forget our final target, which is process optimization and simulation, which was always a target for our group. We started developing the ENSO dynamic process simulator, and now Professor Seki, who is attending here, maintains it and keeps it updated. More recently, we also developed the EASY process simulator. It's a steady state process simulator, which includes these models. So if you want to simulate processes with the models we will discuss today, please visit this website or bookmark it to visit later. You can download the simulator there. It's very easy to use, that's the idea. And you can use these advanced thermodynamic models with it. So about the topic today. Why do I particularly like COSMO-based models? Because you can, in a single step, come from computational chemistry, quantum chemistry, to process engineering in one single step. Of course, there are several approximations to start with the quantum chemistry with COSMO alone, and to end in process engineering, where you compute activity coefficients as a function of temperature and composition, and then apply in thermodynamics in process engineering. So it's really a multi-scale modeling approach. So that's very nice. One problem is, what about pressure? So these models, they don't take into account pressure. And what we recently achieved with the COSMO-SAC-Phi version, or Phi, if you like it that way, COSMO-SAC-Phi, we can actually compute active fugacity coefficients as a function of temperature, pressure, and composition. So this is included in the model, and that's the topic of my presentation today. So what are these COSMO models? For those not used to the technology, people tend to get confused on what's COSMO for real solvents, COSMO-RS or COSMO-SAC. First of all, COSMO alone, just COSMO, is a method for solvation of pure substances in a solvent. So it belongs to a class of what we call the electric continuum models. The solvent is a continuum, and you have the molecule you're interested in. It's put inside this continuum, inside of a cavity, actually. You build a cavity around the molecule, put it inside, and then compute the charges it would induce on this dielectric, usually assuming it's this dielectric is a perfect conductor. So these computations can take a long time, a few minutes for small molecules, or hours for larger molecules, or days if the molecule has dozens of atoms. So what we usually do is to make this computation once and then store the results. These colors are the results, which are the induced charge densities, and then we store in databases. You can visit this website. We keep a database with around 2,000 molecules already computed and freely available. So besides this presentation, I will also demonstrate how to use our package, which is called JCosmo. You can download this package with the link that came with the invitation for this presentation today. I will show you here on my screen. If you download that package and extract the contents, you'll see these files. On Windows, you can double click on this executable here. I'm on Linux right now, so I will run this shell script here. When you do that, you should, in a few seconds, see a graphical interface like this one. We use this for teaching thermodynamics. The students love it because you just search for a compound like acetone, search for the compound, add to the mixture of compounds, and you can see the molecule. These are the apparent surface charge densities. For the acetone, we have oxygen more electron negative than the other atoms, so it will induce a positive charge because it will end negatively charged, so it induces a positive charge. Charge densities always. You see here a nice smooth surface, but actually this is discrete. If we check this box here, show calculated points, and see the surface again, you'll see actually the points where the charge densities were computed. So this is how this works. Every small ball here has charge density, and this is converted to colors so we can see the surfaces. And that's the idea of COSMO alone. And with this information, they calculate solvation properties usually, but not mixture properties. We can check here on this JCosmo application on other compounds, of course. I was looking for chloroform, just to see the surfaces. Here, chloroform, chloride is more electronegative, so the hydrogen will end up positively charged, and then will induce a negative charge, which is blue. That's the idea. But this is for the molecules alone inside of a perfect conductor. This is the COSMO method when they are alone. What is the COSMO-RS? COSMO for real solvents is then when you can apply this model for mixtures. How it actually works, basic idea is around every molecule you have the perfect conductor, and small segments. You could imagine several post-it notes, sticky notes, post-it notes around every molecule. And if you put two of these segments in contact, like here, this one was surrounded by the perfect conductor. This one was also surrounded by the perfect conductor, but in this arrangement here, the perfect conductor was excluded for this part of the surface. And if we keep doing that, putting pairs or segments of all molecules in pair contact with other molecules, you end up with a situation where there is no more perfect conductor between these molecules, and you reach the real solvent or the mixture, the real mixture. And that's the difference between COSMO, which is for molecules alone, isolated molecules, and COSMO-RS for real solvents, or COSMO-SAC, which is basically the same idea. Since we use the COSMO-SAC notation in our papers and code, we tend to call it COSMO-SAC, but it's essentially the same as COSMO for real solvents RS. And every time you put two of these segments in contact, there is an energy involved. So contacts of more energy will end up less likely in the solution, and contacts with less energy or smaller energy will be more likely to occur. And then this is how these models work, is computing these probabilities. You can see there are many possible contacts. If we see the surfaces here, let me turn on the calculated points again. If you see these surfaces, imagine every small ball could be put in contact with every other small ball of the molecules of the same kind and molecules of different types in the solution. And you need to calculate the probabilities of all possible pair contacts in the solution. This is not a simple calculation. So how it's actually done, to avoid the need for molecular dynamics or Monte Carlo, the way we actually do it to avoid this is to first of all to create an histogram with forget the three-dimensional distribution of charges and calculate a histogram where we map every color to a given surface charge density, and we accumulate the amount of area that color actually has. So we have this histogram with charge densities per area, or probability if we want to call it that. Here in the JCosmo application, this is the sigma profile. We see it here for our molecules. Let me show them again. So we have here the sigma profiles for chloroform and acetone. You see they are nearly a perfect match. They are nearly mirror sigma profiles distributions like this. These sigma profiles you see in articles and in tools like this JCosmo tool. You see this nice smooth curve. Actually, this is not how it actually is. They are actually discrete curves. If I check this box here, show the discrete sigma profile and refresh, you see that it's actually discrete. What we do is to get a range of charge densities and accumulate the area which has that charge densities between these two values, and we accumulate that. We end up with sigma profiles like this. This is what is actually taken into account in the computations, but usually they are shown like this. They are nice to see and easy to follow with the eye. And what's nice about this, I always like to quote John Prausnitz here, is if we call these sigma profiles pure compound properties, we end up calculating mixture properties, activity coefficients, or chemical potentials based only on pure compound properties. Using here, of course, a poetic license to call these sigma profiles a pure compound property, since they are also calculated. And with this, we can explain several kinds of deviations, negative deviations from the Howell law, positive deviations. We use these to teach thermodynamics. The students, you love it. In the JCosmo, you can go here to the vapor-liquid equilibrium tab, select one possible vapor-liquid equilibrium. If we go to this negative deviation, it actually is chloroform and tetrahydrofuran. These files here come with the JCosmo distribution. Just go to your JCosmo folder, and then data, vapor-liquid equilibrium, select one experimental data. And then you'll see the experimental data in the COSMO-SAC predictions. You can also check, see other models, for instance, UNIFAC, and recalculate. For this particular case, UNIFAC's a little worse than COSMO-SAC for the prediction of this mixture with negative deviation. The other one behind here with positive deviation is also here, is ethanol and toluene. You see here now UNIFAC has a perfect matching for this experimental data. Probably this data was used on their parameter estimation. And here the predictions for the COSMO-SAC model. In this case, again, very good prediction. Not perfect because this is not a fit, but a prediction. No particular data of this mixture was used to produce this response, and that's the beauty of this method. You have the molecules, and you try to predict the mixtures. Here, some slides just with what I've shown for you, and how it actually works. As I was saying before, every molecule is assumed to be covered or consists of many post-it notes. We call them segments, and we need to put every segment in contact with other segments, and we calculate the probabilities of these contacts. That's the basic idea. How this is actually done is with this equation. We call this equation the self-consistency equation, where the activity coefficient of a given segment, not of a molecule, a segment, one of those post-it notes, depends on the activity coefficient of all other, and here is for all others, all other segments, including this one we are actually calculating, and here is the interaction energy between the segments M and N. So this is a system of equations we must solve, and that's very different from classical explicit models. UNIFAC is relatively complex, but you still can implement it with a simple spreadsheet and a handful of formulas. This cannot, because you need to solve the system of equations. And the size of the system depends on the number of segments you have in the mixture. So it's a system of equations that need to be numerically solved. So that's very different from classical models in this subject. And to get the activity coefficient of a molecule and not a segment, we need to sum all segments of that molecule, subtract the activity coefficient in solution and the activity coefficient of the segment when the substance is pure. Here is the area of a segment. Here is a parameter of the model, a universal parameter of the model. This calculates the residual contribution. And then for the combinatorial contribution, we use things like Florey-Huggins or Staverman-Guggenheim. And that's how these models work. And this ends up as a function of temperature and composition. Okay. There is no pressure involved, mainly because we assume that every surface, parent surface, is in contact with other surfaces. I could not make a drawing without these small empty spaces here, but they should not be there. Cosmo-based models assume there is no empty spaces. All surface segments are in pair contact with other surface segments. So if we reduce the pressure, nothing happens, nothing changes. There's no empty spaces, so pressure is irrelevant. And the volume is always given by the number of molecules times their molecular volume. That's the idea. But that's not enough for several applications. So you have several attempts to combine activity coefficient models with equations of state, so you can have these pressure effects taken into account. And additionally, on the computations I've shown you before, we always assumed the modified Raoult laws. Oh, sorry, Raoult law. We were assuming this in the previous computations, and then you need the saturation pressure. What about if you are above the critical temperature of that compound? So you don't have that saturation pressure, and you cannot use these approximation. So there are various alternatives in the literature. For instance, the non-random Cosmo, the sigma MTC from Kawe and Fred, they are attending here, and combining cubic equations of state with COSMO-SAC. There are several attempts to do that. We did that not long ago using this mixing rule. We are very proud of this mixing rule. We call it self-consistent mixing rule. We have this here in the JCosmo package. I will show you just a moment. Here in vapor liquid equilibrium, let's say we will now check the hydrogen sulfide and water for this case. This will generate an error here because what will happen? I'm using UNIFAC, but UNIFAC cannot handle hydrogen sulfide because it's a supercritical compound in ambient temperature. I must uncheck UNIFAC here to recalculate. And this is assuming the modified Raoult's law, which we should not be using for this case. It's extrapolating a saturation pressure here for the hydrogen sulfide, but this makes no sense at all. And of course, the response is very poor. We can use the self-consistent mixing rule to combine the Cosmo calculations with a cubic equation of state and recalculate this case. It will take a little more time because the calculation is much more complex. You have the fugacity coefficient of liquid and gas or vapor, and the response is much improved. We can use the modified self-consistent mixing rule, which is another model more recently proposed by Professor Lin, which was the original author of COSMO-SAC. They modified our self-consistent mixing rule and called the modified self-consistent mixing rule specifically for the case of light gases. And this will indeed improve a bit the results here, modified. If I check to use the modified self-consistent mixing rule, recalculate, we'll see a result slightly better for this particular case. But what's the problem with these models? For instance, the self-consistent mixing rule didn't work so well for this case, and it tends to start to fail when we have very light gases at high temperatures. The modified self-consistent mixing rule produces a little better results for this case. But it has a drawback. If we go back to low pressure results and we keep the modified self-consistent mixing rule, we see that the results are worsened. and if we use the self-consistent mixing rule, the results are nearly the same with the mixing rule or not. That's the idea of this mixing rule, is to enable to use a mixing rule and do not distort the underlying activity coefficient model. But the self-consistent mixing rule has some difficulties for light gases, and this is better for light gases. So what's going on here? Problem is they are all approximations, and they need something to couple the equation of state with COSMO. And then what we try to do is, what about trying to create a complete new equation of state, and not coupling it with existing ones. The idea was, what about introducing empty spaces? We call them holes, empty spaces between the molecules. And then by doing this, we could, as the pressure is reduced, introduce more holes, more free volume, and then we will see volume differences, which do not occur. We do not see that when in COSMO for real solvents or COSMO-SAC. We call this idea a pseudo mixture, and the interesting thing is you just add another compound in the mixture, and the implementation of COSMO-RS, COSMO-SAC, or F-SAC don't even know that's not a real compound. We can cheat the code and say, well, instead of pure substance, you have a mixture now, and then we calculate activity coefficients or chemical potentials of the compounds and the chemical potential of the holes. That's the important part. Because what's missing here is, what will be this relation? I reduce the pressure, I increase the volume. What will be that relation? That was tricky. So after several days and hours of study, we could show that the pressure, if we model the system this way with a repulsion plus an attraction, we can call it this the reference fluid and this the perturbation fluid. That's another way to see it. And then this attraction pressure, we could show it's the residual chemical potential of the holes divided by the volume, molar volume of the holes. And so when we were very excited with this result, because it's a very simple equation, and very elegant equation, to be honest. And then using the COSMO implementations, the only missing step is how to get residual properties and not usual properties, because in this slide here, we have this residual chemical potential here. This was also solved by using classical thermodynamics approach. If we need to residual, we just need to subtract the ideal gas contribution, and to get an ideal gas, we just need to make the volume go to infinite. And this actually turns out to be very simple to implement, because we already are used to calculate with activity coefficient models. We are used to calculate infinite dilution activity coefficients. So if we calculate this infinite dilution situation, where the compounds are diluted in holes, we have essentially only holes, and then the molecule infinite diluted in it, we get the ideal gas limit. And that was the final step missing to get a complete equation of state with COSMO-based theory. In order to implement that, we faced some problems, because in COSMO implementations, usually you have hydrogen bond, okay, and electrostatic. The electrostatic comes from these sigmas, which are the charge densities, which are the colors. Hydrogen bond, there are some equations to calculate it, but dispersion usually is ignored or oversimplified, and you cannot have an equation of state without dispersion contributions. So we had to add an alternative for that. And we chose the simplest possible model, which is for every segment, actually for every molecule, we say they have a dispersion parameter, and then every time you contact two segments M and N, they have a dispersion which is simply the square root of the dispersion of the segments, which is the classical combining rule. We could even add here a binary interaction parameter if we want. If we really want, we could do that. We don't usually do it, but you could if you want. And then to sum up, we need some parameters for the dispersion. This is the dispersion contribution. We are currently revising this because it's inconsistent for very low temperatures. We just find out that very recently. We are in the process of revising this. This is the volume of a molecule, and this is the volume of the holes. Unfortunately, the volume of holes depends on the molecule I need to model. So it's not a universal parameter. We had to fit that as well for pure compounds. And when we do that, we fit pure compound vapor pressures and liquid volumes, compared here with classical Suave-Hedley-Kong with Matthias Koppelmann. For the pressures, we cannot see any difference, but for the volumes, the difference is huge. Not saying that we should do that that comparison, because we all know this model will be very poor for liquid volumes, but just to have an idea on how it's responding. For slightly larger molecules, the same pressures are perfect, and volumes not so good for instance, for an octane here. Volumes are not so good, but we are using a very poor repulsion contribution. We could introduce a better formula there and perhaps solve this. And also by fixing the dispersion, we could also improve these results, but this work's not published yet. And then with the pure compounds correlated, with the pure compound data correlated, we can predict mixtures at various pressures and kinds of deviations, positive deviations, negative deviations, or nearly ideal cases. Here we have COSMO-SAC-Phi and also COSMO-SAC, just to show that it's nearly the same if the pressure is low. They are very similar. Again, comparing with Suave-Hedley-Kong and van der Waals mixing rule, no binary interaction parameters. Again, not saying it should work, just to give you some idea of what it would produce for these cases, including negative deviations. In this case, where we all know the cubic equations of state without negative binary interaction parameters can never represent negative deviations. And the advantage is we can go to high pressure now without any other equation of state, because the COSMO-SAC-Phi is itself an equation of state, and then we can predict cases with supercritical compounds with positive deviations. Not the case here, because they are both under critical, just the pressure is a little bit higher. Very non-ideal cases like this one, ammonia water. We can use also this model to calculate liquid equilibrium at very high temperatures. Here, high temperature, and of course, as the temperature goes up, in order to keep a liquid equilibrium, the pressure is also going up here as well. Here, pressure is also going up, and we can predict how for instance, the very low mutual solubility of hydrocarbons in water, it increases a lot if the pressure temperature goes up. These are predictions. There is no parameter adjusted for this case. Again, just as a comparison, UNIFAC for liquid. Of course, this is unfair with UNIFAC because it's designed to work around ambient temperature, like just this small range of temperatures, and we are just extrapolating here just to give you an idea of how it would perform. The model can be extended for ternary and arbitrary number of compounds, just a simple ternary result here just to show you how it compares with experimental data. COSMO-SAC-Phi and unifac liquid-liquid for this case, results are very similar. And what gets more interesting now is that we can apply this model for high pressure systems, gas systems, including polar compounds without, or hopefully without, needing binary interaction parameters. For these cases, we have the results for Gerg water with temperature dependent binary interaction parameters. It's the dashed result. CPA with binary interaction parameters doing a very good job without temperature dependent binary interaction parameters, just binary interaction parameters, but parameters adjusted for this particular case. And if we just apply COSMO-SAC-Phi for this mixture, we get results, if not better, but very similar to these correlations. So we got very, very excited about these kind of applications. And that's what we are pursuing more recently. Just another example we started to pursue is the very complex problem of asphaltene precipitation. So asphaltenes, nobody knows exactly, and they are all different, but this is typical molecular architecture. And if we try to apply any COSMO model to something like this, I now know it will fail. You can make it work. Our friends here made it work if you introduce some empirical stuff, but that's not the way we want to go. So what we did, and what is a common mistake in my opinion, is, well, so COSMO works for everything, let's apply to everything, to very complex stuff, and see what it says. We should first try simple mixtures. What would be a simple representation of this? A simple representation for this kind of mixture would be a solid liquid equilibrium of, for instance, let's see, naphthalene benzene, for instance. Here's the experimental data, and we have two curves here. This dash dot is assuming an ideal mixture, and this solid line is COSMO-SAC. Here is the fusion, pure compound fusion, and here's the solubility temperature versus molar fraction. You see that the ideal mixture is doing a better job than COSMO-SAC. How's that? How come? What's going on? If we come here and add naphthalene benzene and view the surfaces, they are very, very similar, right? Electrostatic contribution should be nearly zero. They are nearly identical. If we see here, the sigma profiles are almost identical. What the model will say to us? Well, the electrostatic contribution should be nearly zero. We will have the combinatorial contribution, since these molecules have different sizes. The Flory-Huggins contribution will give us a negative deviation. And that's exactly what we are seeing. What we are seeing here. Negative deviations. Very small negative deviation for naphthalene benzene. And that's the source of the problem. If we get, for instance, anthracene and benzene, the errors increase because anthracene is even larger than naphthalene. Anthracene is even larger, but again, the sigma profile or the colors are essentially the same. So the electrostatic contribution should be nearly zero, and the differences in size increased, so the deviation should be more negative, which is what we are seeing here. But the experimental data says the deviation is positive. So there are stuff not being taken into account here. What if we go to the COSMO-SAC-Phi model? You can check it using our GCosmo development version, which is on Windows, double click on this executable. On Linux, just double click here and run. For the COSMO-SAC-Phi model, I just select here COSMO-SAC-Phi. We have additionally the differences in dispersion and the differences in free volume. And as we will see, if I go back to the anthracene benzene, was that the last one, if I recall, and calculate again, here are the experimental data. It takes a bit longer to calculate because it's an equation of state. You need to solve the fugacity coefficients and then calculate the activity coefficients. And you see now we can capture the positive deviation for this case. Perfectly, we got very surprised about that. These are pure predictions. So not only high pressure cases will benefit of something more advanced with as COSMO-SAC-Phi, but also low pressure systems where we have differences in free volume and differences in potential differences in dispersion. Okay, so to sum up, COSMO-SAC can be extended to become an equation of state by the addition of free volume or holes. The advantages of these, which I think are very important, you don't need to define a lattice, you don't need to arbitrate any coordination number, you don't need no association scheme, which is usually a nightmare to choose for more complex molecules. And we have a proof of concept working with very simple repulsion contribution. It can be used to correlate vapor pressures with a good accuracy. Can be used to calculate liquid-liquid, vapor-liquid, and solid-liquid equilibrium. We are currently working on extending the dispersion contribution. As I said before, the one we had published and implemented has some inconsistencies for very low temperatures. The repulsive contribution, which is classic van der Waals, could be improved. And we are testing other applications with several friends from Silvana from Bahia, Marcos Mafra, Paraná, Roberta Siriani na Unicamp, Marcelo Castier, André Muniz, nosso colaborador, professor Nilo, Folegatti da USP, something with Fred Giordano, and a bit with Professor Castle. So thank you very much for your attention. Don't forget to visit this website where you'll find our database with 2,000 compounds, nearly 2,000 compounds, or visit our webpage for our laboratory. You can contact me or Paula about these subjects. Thank you very much again. I'll be available to discussions or questions you might have. Please feel free.
Thank you, Professor Pelegrini, for an excellent presentation. And we are now open for questions. If you want to ask one, please enable your microphone or write down in the chat and read it. And your YouTube viewers can write down also, of course. So I think Ingrid, the Professor Lirio has a question.
Please, Professor. In the chat.
The question is,
Alirio, open your camera, please.
Sorry, I missed the chat.
Okay, Professor.
Okay.
Is there a limit in the number of components in the liquid mixture for the vapor-liquid predictions? On this particular tool I showed you, it's only for binary mixtures, but the activity coefficients can be calculated for any number of compounds. For these cases, we provide some interfaces in MATLAB, Python, Java, where users can request for the activity coefficient and then calculate the equilibrium for arbitrary number of compounds. So it's not limited to binary or ternary mixtures. But this graphical interface I was showing you is limited to binary for the vapor liquid and ternary for liquid.
Thank you.
So do we have?
I could ask some more, several questions actually. I'm very.
Go ahead.
So Rafael, I think we met in Cordoba. Is that right?
Yeah, right.
Okay.
Nice to see you again.
Yes, my pleasure. So let me see. I have to check my notes. So you said you have 2,000 compounds characterized, right?
Yeah, that's correct.
And so that's similar to what Virginia Tech had characterized too, right?
Yeah, they have 1,500, something like that. Very similar.
Okay.
The problem we chose to not use or not start or extend their database because they used closed source, very expensive for us here in Brazil, software. So we decided to go with games, with it's open source and free. So we had to start from scratch. Otherwise, we would just it would be easier to just extend their database, but we couldn't.
I see. Yes. Yeah. That's was one of the questions was, how important is it to be consistent? It's not possible to mix and match the sigma profiles, is it?
Yeah, you cannot mix sigma profiles. Even if you choose the exact same parameters, there's no guarantee that the implementation will produce exact the same sigma profile. So it's not a good idea to mix sigma profiles from different software. And what we usually do is for every software, we recalibrate the universal, the so-called universal parameters. You have a dozen of parameters called universal, and you need to recalibrate for every database of sigma profiles.
Okay, so but one of the things that I liked about the Virginia Tech website for this was that they also provided the Fortran code for computing the activity coefficients from the sigma profiles.
Yeah, that was very nice. It was also our starting point. And okay. I believe it was the starting point for many different groups. That was very nice.
Yeah, so I actually implemented that, and there's an example in our textbook. I don't know if you're aware of it.
I haven't seen the latest version yet. No.
Oh, okay. Okay, yeah. So check out the second edition. Yeah. So yeah, I'm a big fan of this Cosmo approach, and like you say though, it's hard to implement if you don't have access to the ability to generate your own sigma profiles and stuff. But one thing, when I went through that Fortran program and implemented it for like an example in the textbook, I don't remember solving a large system, a matrix system of equations to get the segmental activity coefficients. It's more like a summation is what I recall, maybe a double sum over, multiple elements.
This particular system is very, very curious in the numerically speaking, because although you need to solve a large system of equations, one might think, where is the matrix? Where is the Jacobian I need to invert to solve this system, right? So this particular problem can be rearranged, and then a simple successive substitution can solve the problem. So you don't actually see in that code. We have a paper specifically about that. We tried to solve using Newton-Raphson method, and we actually shown that for if the number of compounds in the mixture grows, it's actually better to use the successive substitution than using the Newton method, which was very surprising to us, because one would think, if I have the Jacobian matrix and I invert it, it should be faster to use Newton-Raphson, and it actually is not. So that was very surprising. It was very hard to publish that paper because it's one of those papers you suggest something and just show it doesn't work. So, but the point was people will try to do that again and waste their time. So we have that paper published.
So that's like a Gauss-Seidel. That's the method of successive substitutions for a matrix?
Yeah, it's similar, but in this case, you don't even need the matrix. It's very curious. You can rearrange the system, and you don't even, in the end, don't even need to build a matrix, which would be a dense matrix and occupy a fair number of bytes, let's say this way. It's very interesting that the way people solve it.
Okay. Well, okay. So let me just ask one more practical question. So I think I mentioned way back when that we would want to evaluate this method as part of the properties of gases and liquids, and so I think you had even might have sent me some code long ago. It's taking us longer to get this done than I would have hoped, but it's coming along, and we're ready to do mixtures now. So, so just
nice. Please keep in touch. We would love to try to contribute and help somehow. Also,
yeah, we need some
very glad to see it on your book or something in that sort.
Okay. So we'll be in touch. Thank you.
Great. Thank you again.
So I think Professor Martin Sismond raised his hand, right?
Yes, thank you.
So you can go.
Hi, Martin.
Rafael. Hi.
Hello.
Thank you. It was a very interesting presentation. I think after each of your talks, I'm slowly getting a better idea of what these approaches are and how they work. Was very interesting. Just two simple questions or comments. In several examples, for example, one in slide 26, I remember, I think it was a PXY plot or diagram. That was one of the cases where you have this incomplete and this strange result that are typical to see in some cases. And
something like this.
Yeah, that one on the right. So and when you have experience with this, you know that implies three-phase equilibrium, liquid vapor, right? So, but this is what you get when you just continue the solution, the mathematical solution for the two-phase equilibrium.
Yeah.
So. This is one of the cases where, but I don't know how is the algorithm you have for this, but maybe this algorithm could be improved and could benefit from some strategy similar to what we have in JPEG, for when you first locate the three-phase equilibrium, and from that point, then
you walk the path, right?
Yeah, exactly. And maybe that's an opportunity to improve and complete those cases that from time to time you get.
Yeah, our implementation for these equilibriums is very, very simple. It just goes increasing the molar fraction of the first compound and computing the pressure. So it's definitely not correct here. You see, you should start. You should see a liquid. In this case, where we have this strange thing here. We also have some difficulty in closing the critical point with our algorithms. We are very aware, you and your group, you excel at that. You have those magnificent charts with multiple phases. it's not our specialty, so we for now at least use very, very simple computations. We definitely could improve from that. I'm not sure it would be so easy because if you use cubic equations of state only, they are simpler and it's easier to get several partial derivatives. You need to implement those path following. I don't know how do you call it, but path following or something like that.
Yeah, or continuation method or something.
Yeah. And for this COSMO-SAC-Phi equation of state, it's more likely SAFT in the sense that you don't have several of those derivatives because you need to solve a system of equations every time you need the fugacity. So to get the derivatives of it, you will need to make perturbations. You don't have those derivatives, at least not right away. And I believe it would be very hard to implement that. No, I'm not sure I'm correct. You could please correct me if I'm wrong.
Maybe an opportunity for future collaboration with some
Sure.
student. Who knows?
That would be great.
And
because we definitely don't know how to do that.
it can be interesting to discuss it deeper someday. But the other simple observation, when you mentioned asphaltenes and what you were trying, I agree with your approach that before going to very complex molecules in detail, to study first simple or simpler molecules that show the qualitative phase behavior or phenomenology, right? But more than mixtures of, and it can be okay to take anthracene or what was the other one?
Naphthalene
or naphthalene, and so a simple example of these very aromatic molecules like asphaltenes. But I think it can be more interesting to show what you have with asphaltenes in reservoir fluids, to study the mixtures of those components with alkanes. So you can have a phase split and probably a liquid-liquid phase split closer to what you have in reality in reservoir fluids.
Yeah, we have
that's a suggestion, maybe to
there was one other example I would like to show, but I forgot. When you try with an alkane, so COSMO alone is able to predict a positive deviation, but again wrong. And COSMO-SAC-Phi for this same case is with butane. It again produces a perfect matching. It was very, very surprising. The right positive deviation. Of course, we are computing here again with a very simple algorithm, just the solid liquid, not predicting any possible liquid here. But yeah, that's very important for this particular application. Thanks for mentioning it.
Interesting. Thank you.
Thanks again, Martin. Hope to see you soon in person.
Okay, so we have a quick question from our YouTube. Can I read it?
Yes, please.
It's from Igor Pereira. He thanks you for the presentation and asks you what is the shape of the empty space and if they are spherical.
Very, very nice question. They are not spherical and we don't know the shape. There is no shape. If we define a shape, then we could make a relation between area and volume. Like in a sphere, if you know the area, you know the volume. We tried that several times, several different attempts, and we could not define a shape. So we just, at least for now, we gave up and we adjust the volume of the free volume, the volume of the holes. and we gave up trying to put a shape on it, at least for now. Maybe someone can try that again or have another ideas, but for now we don't have an actual shape for the volume.
Okay, thank you.
I have a question.
Please, Matt, go on.
We have two people in the line, Professor, so we can
No,
invite them.
go ahead.
Okay, so Esteban asked to...
Okay, thank you very much, and it was a very nice talk. We do a lot of separations in Chile and in the University of Santiago de Chile. We use a lot of... there's someone else talking. We do a lot of COSMO-SAC-Phi, you know, and it is we know that sometimes COSMO-SAC-Phi doesn't predict very well when you have molecules with a lot of chlorine atoms, right? Have you studied that? How about your predictions when you use molecules with a lot of chlorine atoms? For example, some emerging pollutants, PCBs, polychlorinated bisphenyls, dioxins.
We haven't tested it yet to say how our implementation would work, but for sure, Cosmo will have some difficulties. For instance, that I have tested, and I know, for instance, if we have several fluorine with the perfluorine gases, since the usual way to model it disregards or oversimplify dispersion, and you have very different atoms, they are not much polar, so they end up with nearly zero induced charge. So Cosmo will think they are hydrocarbons, and they are not. So definitely the dispersion contribution, I think, would help in this case, as it helps in the fluorine compounds. But I couldn't say because I haven't tested these particular compounds you mentioned. But it will probably have some difficulty because of the dispersion, which is usually very, very poor.
Thanks.
Thanks, Esteban. Okay, so I think Simon Muller is the next. You can go on.
Yes, thank you. Thank you also for the nice talk. I had a question. Up to what pressures have you already applied COSMO-SAC-Phi?
We have applied to 200 bar. I don't exactly recall it, but something like that, 100, 200 bar, and haven't actually looked for the limit. To be honest, I don't know if there is a limit or what would be this limit, but I just recall from the top of my head, like something 200 bar, 200 atmospheres, stuff like that.
Okay, thank you. And then one last question. I know from your paper that you have read the paper about COSMO-SAC, where they include basically density dependence when they calculate the COSMOS space equation. And I'm interested to hear what do you think about the approach, or
but the approach was limited to infinite dilution, wasn't it? If I recall correctly.
Yes, they applied it. Yes, they applied it to infinite dilution. But I was more interested in the general idea of making the interactions a function of, for example, the packing fraction or something like that.
I'm not sure. Once I learned it was designed for infinite dilution, I'm actually did not go that deeper to know and to give you an opinion on what they actually did. These papers are usually very, very hard to follow. I hope my presentation was, I skipped several details to make it easier to follow, but this topic is very complex. And for instance, if you get this NR Cosmo here, I challenge anyone here to understand what this paper says.
Yeah, I also read problems.
So we need to be selective, and once I learned they had this limitation, and we are mostly interested in mixtures. To be honest, I don't really know the details of COSMO-SAC. Sorry about that.
Yeah. Okay. Thank you very much.
Thanks, Simon.
Okay, now you can go, Professor, and then we'll have one last question from Professor Richard, right?
Let Richard ask it first.
Okay, so
Richard,
Professor
you can go
Richard?
first.
All right. Okay. Thanks. So
I'm also interested in this question, so that's okay.
Okay. So well, you could ask it then, but
no. Go ahead.
So Andreas Klomp published a paper either 2019 or 2018 where he extended his COSMO-RS method to interfacial tension interfaces.
Mm-hmm.
And the key ingredient that he had to add was some sensitivity to pressure. And so that's what I understand so far, is that sort of what you've added with your Phi edition. And so I'd wondered if you'd seen that paper, if you could comment about how his extension of pressure was similar to how your extension in Phi was.
Mm-hmm. I'm not aware of that work, to be honest. We don't have addressed interfacial tension yet, so I was not aware, and also was not aware there are any similarity between the methods. So I unfortunately cannot comment if they are similar or not. But in some papers, they calculate vapor pressures in a way I think it's completely wrong. Sorry to say that, but so I don't know. I would have to read that paper, but the vapor pressures they compute long ago for me makes no sense at all. But,
no sense.
Yeah.
I agree.
One more thing, slide in here. So another thing that Klump does, he's able to use this Cosmo approach for polymers and biomolecules like pharmaceuticals, and so those are at least as large as anthracene,
Mm-hmm.
or as large as asphaltene. And so I was wondering, is there what is it that, how come he can do this, but you say Cosmo can't do it at all? I don't understand that.
No, it probably can do if the dispersion and free volume is not an important variable.
Oh.
So if it's mostly hydrogen bonding and electrostatic contributions, I think you get reasonable results. But if the forces that drive the processes are mainly dispersion, and if free volume is a key aspect, I think most implementations today will fail because they simply don't take that in account, or take in a very, very poor way. That's what I tried to say before. So you probably can apply. We tried to extend it to polymers, but in a first attempt, we could not get good results. Maybe there is something wrong yet when we tried that extension. For talking about COSMO-SAC-Phi, yes. COSMO-SAC alone, we have applied to polymers long ago. I think there's a paper for 5-6 years ago applying COSMO-SAC to polymers. We identify the repeating unit, and then we compute just this repeating unit, and then multiply this sigma profile of this repeating unit many times, and then we could at least reasonably predict vapor liquid equilibrium between polymers and solvents using that method. But for COSMO-SAC-Phi, we could not yet come up with an implementation. I think it's a problem with the code, actually, not actually a problem with the theory. Although we use van der Waals for the repulsion, we probably need to revise that as well to handle polymers. So it's something we might try again in a near future.
Okay, very interesting. Thank you.
Thanks again, Professor Richard.
Okay, now you can go, Professor.
Thank you. Rafael, congratulations for your presentation. I think it's very nice and like simulating people asking a lot of questions, and I think the everybody that are attending and haven't seen Cosmo yet learn a lot about this today. Congratulations for your presentation. I wonder, I have several questions, but I'm trying to concentrate. One is about the COSMO-SAC-Phi. I wonder about the critical point. How, well, you said that you cannot calculate the critical point, but that's numerical stuff, so I'm not worried about. But I do worry about how it approaches the critical point, and if you use the critical point to estimate the parameters. And similar to this, we are calculate kind of electrostatic interactions. So we do need dielectric constants. And when you put a rho on it, you change the dielectric constant. And you have dielectric constant for vapor phase and dielectric constant for liquid phase. And when you mixture, you have other dielectric constant. So I wonder how you deal with this problem. So it's about the COSMO-SAC-Phi.
Okay, great. About the critical point, COSMO-SAC-Phi is very similar. The responses are very similar to cubic and very similar to Saft-like equations. So we cannot approach correctly the critical point. And even in the, taking this into account, we usually don't correlate the parameters up to the critical point. We stop at 90% of the critical point because we will miss the critical point. So the problem is the same. It doesn't solve the problem we see with Saft, CPA, cubic, etc. It's just the same, or very, very similar to those. So we miss the critical point. We over-predicted. If we correlate with low temperature data at the critical point, we just miss it. About the electric constant, yeah, we use single dielectric constant. We know it should be different for different mixtures. For vapor phase, it should be completely another value, but we use just a single number, and probably the parameters we are estimating are compensating for it somehow. But if someone wants to go that way, it will make the implementation more complex, because if it depends on the composition, it makes several things much more complex. The convergence of the system will become more complex. But it's probably something someone might want to explore. We haven't tried to go that way, and I'm not sure if it will work or it will improve or not. But there are several systems we know are not well represented by these models, and several we don't know the source. We don't have an explanation, and some are very simple. For instance, water and methanol, you can predict the vapor liquid, but you miss the enthalpy of the mixture or mixing enthalpy by a large percentage, and stuff like that. We don't really know what's the missing point.
Maybe you are right. You are compensate with the parameter. Yeah.
Probably.
I also, well, one thing that bother me with Cosmo is you do very nice calculation about the charge concentration of the 3D dimensional surfaces. So it's very nice information, but you break down this and put in 1D and calculate 1D model. That's, well, even for classical Cosmo, it bothered me. So I wonder, do you think that we may have some advantage in use 3D information instead of break down this information in 1D?
Yeah, very, very nice question. We do that to avoid the molecular dynamics or Monte Carlo. We could do that using Monte Carlo, for instance. Getting every molecule, let's get these molecules here, show points. And put every small ball of these in contact with the other one and calculate the equilibrium or the activity coefficient or whatever property we want using Monte Carlo. We could do that. I think the response would be very similar if we are using these two molecules here, because their surface is mostly exposed. But if you have regions or portions of the molecule that can be hidden, particularly if you have two molecules with several branches, maybe you will capture, if you keep the three-dimensional surface, you capture some information that we are currently missing. But for instance, for these two here, I would say, just an educated guess, no, I'm not sure, of course I haven't done it, that the response would be essentially the same. But for more complicated molecules, for biomolecules, for flexible molecules, probably you will be able to catch some information that we are missing, definitely missing.
Okay. My last question is about clumps. Andres, we know that normally he's not happy with people that show some calculations, or even worse, provide information for people abroad, use these say without paying anything profit for him. So my question is, only by curiosity, do you have any problem with him?
Yeah. We had several problems with him. It started well, to be fair, when we developed this FSAC model, which is a competitor, let's say this way, a competitor to UNIFAC. This model is it uses all the theory of Cosmo theory, but the sigma profiles are artificial. We adjust the sigma profiles. And with this, we get very nice correlations for mixtures, and the parameters are for pure functional groups. So I still think this model can be very successful for engineering, because you can correlate data and predict later data using functional groups and using Cosmo theory instead, the UNIFAC approximation, UNIQUAC's approximation. And this is let's say the solution, the real solution. So it started well. He congratulated us on this work, liked it very much. But as the time passed, as we started to provide sigma profiles freely and started to give people code for free, we had an open source version of this package I distributed to you, and couples of years old, is open source, so you can download and see the source of this. Not exactly this version, but for a couple of years ago, it's available on the internet. As we started to provide more free stuff and use open source packages, the problems started to escalate. And the last issue we had, I had to report to the intellectual property department in my university because they got in contact and several problems. But this now is 2 years ago, I guess, and then after that, no more contact. So, but yeah, it's not a good relation for sure. Probably we will never be. So I let it this way.
Okay, thank you, Phil. Nice presentation.
Thanks again, Fred. Thank you for having me. Thank you for the attention of all people, for the questions. Always a pleasure to be here with you, Fred, as well. So hope to see you in a year, maybe in person.
Yeah, sure.
Right, so before we wrap it up, we have one last nice question from Professor Ajmir. He wrote down in the chat that if you are using this very nice and didactic presentation in your undergrad classes.
I'm using this software I'm using in this presentation we use with undergrads. They love to see the molecules and understand why you have a positive deviation, why you have a negative deviation, why some mixtures should be ideal mixtures and some should not, why molecules like each other. So we use a lot this in undergraduate and also graduate thermodynamic courses, and I encourage you to try as well. You can download, send the links to your students, see the molecules. They really like it.
Okay. Once again, thank you, Professor Rafael.
Thanks for having me.